So hello everyone. I'm going to present a joint work with Anni-Yasmin Turhan, and it's about relaxed regular path queries and lightweight DLs. And I'm going to start introducing just some basic notions that will be needed later on to explain what is this topic about. So I will start right away with regular path queries and graph databases. Okay. So first, so let me introduce what a graph database is. In general, one can see a graph database as a labeled graph where the nodes of the graph are the elements of the data and the edges are labeled with relations between these nodes. One can also have labels on the nodes stating the attributes or properties of these nodes. For this talk, I will not use these labels because for simplicity, but all the results hold for them. Now, regular path queries are defined using regular expressions or non-deterministic finite automaton and are of this form. We have two variables and the atom, which is represented by the non-deterministic finite automata or a regular expression, and which is depicted here. In this talk, I will only use non-deterministic finite automata because I will only talk about upper bound. So every upper bound for automata representation holds for a regular expression representation. And the semantics of regular path queries over graph databases is the answers of these queries are all the pairs of elements in the data that are connected by a path whose label complies with the language required by the automaton. In this case, we have only one answer, which is this one here. So R1 is a word that belongs to the language of R1 of this automaton, and C and D are connected by R1. There is no more answer there. In addition to regular path queries, there are also the extensions to two-way regular path queries and conjunctive queries. The first one allows to use inverse labels, allows to traverse the graph in the inverse way, and conjunctive queries to have conjunction of atoms. And just small examples. So this is the query before with an additional atom, and here we have a quantifier variable, which is y. And in this case, the semantics is if one fixes two elements of the data, A and B, and to see if this pair is an answer of the query, one has to consider all the map. One has to see if there is a mapping of the quantifier variables into the data such that these two elements here and these two elements here comply both with the two different automata. And in this case, there is no answer for the conjunctive queries. Now I'm going to introduce the DLs that we are going to consider very quickly. So we are interested in ELH, which constraint descriptions can be built inductively using this grammar here. And Thibault's assertions are of the form, so GCIs between constant descriptions, and there are also role assertions. We will also look at DLite R, and here we have two kinds of concepts, basic and general concepts depicted with these syntactic rules. And Thibault's assertions are GCIs of this form. So the left-hand side has to be a basic concept and the right-hand side a general concept, and similar for role assertions. And finally, a knowledge base is a pair consisting of a T box and an A box, and the A box is a finite set of assertions. And here we have an A box and the graphical representation, which is actually the graph database that we showed before. And so A boxes and graph databases can be translated into each other in general. So from now on, we will just use an A box to explain the next point. Now, I showed you before an example of a conjunctive query of conjunctive regular path queries and graph databases, and now in ontology mediated query settings, the open world assumption is considered, and all models of the knowledge base are considered to define the certain answers of the query. And this is defined as those tuples such that there is a match for every model of the knowledge base. So one can find a mapping of the quantified variables that when we apply this mapping to the atoms of the query, they comply with the respecting automatons. And in particular for this lightweight description logics, there is a very important property, which is that they admit the canonical model, which is a model that can be embedded into all other models of the knowledge base. And the consequence of this is that to compute the certain answers, one that does not need to look at all the models, but only at these models. And many algorithms are based on this property. This is just the continuation of the example. Here we have the same automatons, the same query, Q2, and we have a T-box here. And now with this GCI here in the T-box, we know that if an element has an R1 successor, it must have an R2 successor. And this means that there is this edge with the inverse row. And now, if we consider, if we map the quantified variable to D, then we can find an answer that wasn't before. So CD now is an answer because it satisfies the first automaton, so X and Z with R1, and it also satisfies this one with R2 minus and R1. So the information provided in the automaton in the T-box allows the hidden information allows to find a new path that didn't exist before. Now let's move to the approximate setting, and I just want to briefly give an overview of why this has been studied and what is the state of the art, so to say. So regular path queries were introduced for graph databases and semi-structured data. And one problem that presented at that time is that the data is irregular and is continuously evolving. So it's difficult, sometimes many of the formulated queries, the user doesn't know the exact structure of the path, of the order of the edges, and may formulate queries which are not, which provide empty answers. So the idea is that it's useful to try to relax this query to retrieve more answers than the ones in the classical sense. And the general idea that has been considered is that if two elements are not connected by a path required by the automaton, one can consider paths that are close enough to those required by the query. And the idea is to quantify how close this path is from one that is actually in the language defined by the query, how far away it is. So there are many approaches that has been proposed in the earlier days of graph databases. There was an approach proposed by Jagadish, Mendelssohn, and Milo, which is I'm not going to give the detail, but this is based on a set of rules that describe transformations that says which paths are allowed and how close are they. The problem with this approach is that is really general and powerful, and then is undecidable. And then after that, many people try to find new ways to approximate the semantics that were decidable, tractable. And in particular, there is one which uses weighted transducer, and is the one that we are going to look here. And one of the good things of this approach is that it's tractable for the graph database setting, and also it uses weighted transducers, which is transducers are the natural way to transform regular languages, and weighted transducers and weighted automata is the natural extension of the classical setting to the weighted setting for regular languages. And besides that, there has been a few attempts to approximate the semantics in the ontology-mediated query. One is the relaxing trans queries, which is a very particular case of regular path queries, just concept queries. And another one is one that actually uses regular path queries, but is restricted to a very simple setting where only acyclic ontologies using RDF schema are used. So the idea of the goal, what we want to do is to integrate this approach using weighted transducer to the ontology mediated query setting, in particular for ontology language formulating in EL and DL light. Now, just to give an idea of what how this weighted transducer approach works, let me first show a to explain what the transducer is. And the transducer used in the paper I mentioned before, they are restricted to the tropical semi-ring. I'm not going to talk about semi-rings, but it's not for arbitrary semi-rings. So this is a transducer, it's on a machine, and what it does is it takes an input word, it produces an output word and a cost that tells you the distortion of one word into another. For example, if the input is R1, we have two edges here. This is the input R1, this is an epsilon edge, an epsilon, and the output word here is S2, S1, and the cost of this distortion is 5. Just let's put it here on the left. Another example is here in this path. We have an input word S1 R1 and the output is S2 R1 and the cost is 1. Now, the idea of Grahne and Thomo is to use the transducer as approximation mechanism and to put it in between the query and the database. So we have a query here that I showed you before, we have a database, and now one can see that AD is not an answer of the query because there is no path, because none of this path belongs to the language of the automaton. But with the transducer, we can approximate this in the following way. So we know that R1 and SR1, actually these ones here, they belong to the language required by the automaton. And we know that AD are connected by S2, S1 and S2, R1. So this means that—
Sorry, you have 2 minutes.
2 minutes, okay. So the idea is that this, so the transducer tells you what you can translate and what is the cost. And in this case, there are 2 possible ways, and you take the small one to the smallest one to define the cost. So this is the things, and things that can be expressed is you can extend the classical semantic using neutron transitions like this one, and you can also use Excel translations to simulate the distance. Now, I'm going to skip this very quickly. So we extend the semantics to conjunctives to regular path queries. We have to consider quantified variables and also to consider how to combine the different atoms. For this, we use a combining function with certain properties. And then we define the approximate semantics as a mapping that gives the best cost. And this paper provides an instance of this more general framework that uses a distance and so on. Then we extend it to knowledge bases. And for this, we have to consider the open world assumption. And what we did is that we consider an upper bound on approximation cost. So we consider all the models and take the worst cost. And again, for this lightweight description logics, one can again look only at the canonical model. This was an example to explain what happens when we combine the 2 approaches, how to use the approximation and also the information provided by the ontology, the GCIs. And we define 2 reasoning problems, the T-entailment problem, so that given the tuple and the threshold value, ask whether the cost of this tuple, the approximation cost is smaller than this threshold. And the second one, a computation problem which computes actually the cost. And our results, by the time we submitted the DL paper, were the following. So first, the distortion costs using a transducer, this is equivalent to finding the shortest path in a weighted graph. And this graph uses the canonical model, the automata and the transducer, and of course it can be infinite. For this reason, we had to compute this shortest path in a symbolic way, and for this, we use the loop computation idea used for the classical semantics, for the regular path queries in this logic, but in the classical semantics. And we prove that we can solve these problems polynomial time for two-way regular path queries. For conjunctive two-way regular path queries, what we did, we showed that we can actually bound the depth of the canonical model that we need to answer the queries, and we showed that the depth, we only need depth exponential, and with this we were able to provide polynomial time algorithms in data complexity and non-deterministic exponential time algorithm in combined complexity, and also for the computation problem, polynomial and double exponential time in data combined complexity. So these are our results. Just to finish, in the meantime, we have already improved the upper bounds. We proved that for two regular path queries in DLR, we can decide the entailment problem in non-deterministic logarithmic space, and we found a way to use the bound on the depth of the model to come out with a P-space algorithm for data complexity. And these bounds, upper bounds, are tight in the sense that the problem is NL complete and P-space complete, that were most of the open bounds that were left open. And for the future, we are interested in considering what happens if we. So these are the results for the computational problem, and we are interested in considering what happens with other semi-rings. No, that's all.